Hello, and welcome to the first Zoomcast of the ESE Fall Seminar Series. To kick off this series, we were joined by our very own Dr. Shankar, Director and Professor of Energy Systems Engineering at Lehigh. The seminar, titled The Electricity Utility Landscape, Digitization, Decentralization, and Decarbonization, referred to as the 3 Ds, discussed how power generation will adapt in the face of climate change, discusses some current changes that are already underway in the electricity sector, and also the challenges that we are facing. So to begin, Dr. Shankar touched on the relationship between electricity and GDP by showing the linear relationship between prosperity and access to electricity that the US and Western Europe saw in the 20th century and China and India saw in the 21st century. Countries experienced unprecedented economic growth that was directly linked to having reliable electricity. However, this growth has also led to unprecedented climate change as well. So, Joby, can you elaborate on this a bit more and also touch on the United States generation portfolio?
Yes, thank you, Ava. The United States boasts a diverse mix of fuel generation resources that powers our electricity grid. According to Dr. Shankar's lecture, our fuel generation sources produce 4.1 billion megawatt hours of energy, positioning us with India and China as one of the highest energy producing countries in the world. Fuel diversity is one of the country's key strengths when it comes to energy production and reliability. The U.S. has an abundant access to a wide range of energy sources, including fossil fuels like coal, natural gas, oil, as well as renewable resources such as wind, solar, hydroelectric, and geothermal energy. This varied energy portfolio offers flexibility in meeting the nation's electricity demands and helps ensure a stable power supply, even in the face of market fluctuations or supply disruptions. Moreover, this diversity allows for the implementation of cleaner energy sources, which will mitigate the environmental impact of electricity generation. Despite the U.S.'s diverse mix of energy sources, the United States has faced environmental challenges linked to its energy generation. The extensive reliance on carbon-based fuels for electricity production has contributed to greenhouse gas emissions, exacerbating climate change. However, the nation has increasingly recognized the imperative to mitigate climate change by transitioning to cleaner energy sources. With the world's largest fleet of nuclear reactors, the U.S. has also positioned itself to utilize nuclear energy to address the adverse effects of CO2 emissions. Nuclear power offers a clean and steady source of electricity generation with a minimum carbon footprint, making it a viable component of the nation's efforts to transition to a more sustainable and low-carbon energy future.
Thank you, Job. An electric grid or power grid is an interconnected network of different electric components designed for delivering electrical energy from power generation stations to consumers. Based on technological advancement, the electric grid can be classified into 2 types: conventional power grid and smart grid. Conventional power grid is a centralized electric grid systems in which electric power flows in one direction. Hence, in the conventional grid, electric power flows from the generating station through the transmissions and the distribution system to the end consumers. The conventional electric grid is also referred to as traditional grid. On the other hand, smart grid is an electric power grid equipped with automation, communication, and other IT systems. These additional mechanisms can monitor power flow in the grid from points of generation to points of consumption. Also, they help to control the power flow or to regulate the load to match generation in real time or near real time. The smart grid is a decentralized system where power flows in both directions, from generating station through transmissions and the distribution system to consumers and vice versa.
Thank you, Ahmed. The base of a change in the energy sector towards low carbon emission is the 3D principle, which refer to digitalization, decarbonization, and decentralization. It has been accelerating in recent years, driven by various factors. These 3 interrelated trends are reshaping the energy landscape and facilitating the energy transition to a more sustainable and low-carbon energy system, as will be elaborated detailed by Jessica and Mike and Ava.
Thanks, Mohammed. So, as he mentioned in the seminar, Dr. Shankar discussed the 3 Ds needed to transform our current electric utility landscape: digitization, decarbonization, and decentralization. And these are required as we transition from our current electric utility landscape to one that can support dynamic loads flowing in different directions, both to and from consumers. So I'll discuss digitization and then pass it off to Mike for decentralization. Digitization is an update process that uses sensors, increased connectivity, and data tracking to dynamically provide feedback on grid operations in real time. So these sensors can include temperature sensors, point load sensors, and flow sensors to understand if regions of the grid are drawing power or producing power. So as an example, as people put solar panels on their homes and install batteries that are connected to the grid, the supporting infrastructure needs to change, and we need to understand how these items are interacting with the grid. So in an effort to understand the loads that are being added to the grid, as well as the changing needs of customers, digitization is necessary. And being able to monitor real-time needs of individual customers and quickly communicate with them and receive feedback can better add to their service from utility companies. So by adding digital sensors to actively monitor the grid through a territory while providing real-time data, these utilities will be able to accept changing loads into the grid and dynamically feed power where it's needed. Digitization will also allow utilities to better monitor outages in real time and address them accordingly. However, it cannot single-handedly transform the electric utility landscape. So Mike will talk about another aspect that's required: decentralization, which also plays a key role.
Thanks, Jessica. As previously mentioned, the second D is decentralization. Traditionally, the grid has worked one way from power plant to substation to the home. With home commercial solar, wind farms, geothermal power becoming more prevalent, the modern grid is evolving into a web of distributed energy resources. Dr. Shankar believed that the best way to handle all the distributed energy resources is to make use of a virtual power plant. A virtual power plant combines the monitoring and sensors that Jessica mentioned for digitization with distributed energy resources. Being able to accurately track and meet our energy demands will greatly increase the efficiency of the energy grid, lowering carbon emissions. However, further action must be taken to meet our climate change goals. So I'll hand it back to Ava to talk about decarbonization.
Thanks, Mike. So decarbonization describes our efforts to reduce and eliminate carbon-based fuels from our generation portfolio in an attempt to mitigate the effects of climate change. Dr. Shankar highlighted that decarbonization imperatives are really the key drivers behind digitization and decentralization. Carbon reductions under the IPCC require global temperatures to be no more than 1.5 to 2 degrees centigrade above baseline. And to be quite frank, we are very much falling short of this goal. So unfortunately, efforts to decarbonize by the top 3 polluters, which is the US, India, and China, must be voluntary. We can't simply force people to make these changes, even when the threats of climate change are what I would say blatantly clear. So a critical factor for success in this realm will be international cooperation. Electrification is one solution for decarbonization, but the generation source must also be carbon-free for this to have an impact. Electrification will also drastically increase load, so there must also be efforts to shave peak demand and improve energy efficiency. I felt the frustration of figuring out decarbonization strategies firsthand during a project last semester in transmission and distribution, where we were tasked with getting New York City to be net zero by 2050. And the main conclusions that groups drew from that exercise were that decarbonization was going to be very expensive any way that we looked at it, and that we are still in need of many technological advancements and research and development, especially in the realm of energy storage. And then also that the best solution would most likely involve more nuclear power in addition to renewables. So knowing that the technology for carbon capture of fossil fuels has fallen short, I think this also makes nuclear appear to be a more attractive option. So Jessica, do you want to discuss the case a little bit more for nuclear power?
Sure, Ava. I definitely agree with you that nuclear energy was rightfully touched upon in its own section in the lecture as potentially the solution for our future energy challenges and needs. And a key issue with transitioning, as you mentioned, to renewable forms of energy is their inconsistency and unreliability, and in comparison to the non-renewable forms of energy that we rely on now. As an example that we touched upon in class and during the lecture, solar energy is only produced during the hours of the day when the sun is higher in the sky. So solar plants typically go offline and stop generating just as the peak evening demand hours begin, which is where the issue lies. So this creates a steep-walled duck curve, which requires the high ramp rates and speeds from dispatchable sources of energy like natural gas, coal, and to some extent nuclear as well. So this curve and its slope demand for dispatchable energy is the most extreme in California, where solar energy can meet a majority of energy needs during the day, but quickly goes offline. So this points to a non-renewable plant replacement that we would need in place of coal plants and natural gas plants that are able to come online quickly to produce high demand energy during those hours. So nuclear, even though it might not see the same ramp rates, can produce this energy in the evening with less pollution compared to non-renewable plants like coal power plants ramping up at a high speed, which ends up creating more pollution. So installing more nuclear power generation would alleviate a lot of these subsequent pollution issues currently and observed in California. So otherwise, non-renewable power plants cannot be phased out while there's still no other form of dispatchable energy to take their place. Now, it's important to note that nuclear energy comes with many of its own challenges, most notably the public acceptance of nuclear in the United States. Following a few nuclear reactor incidents, including the 3 Mile Island meltdown in Pennsylvania, a distrust of nuclear energy grew amongst the American public, and this has prevented new power plants from being approved and built, while other countries like France have grown their nuclear capacity and decommissioned old power plants. So the public acceptance roadblock has severely handicapped the US in its ability to transition away from non-renewable technologies. Overall, nuclear can solve some of America's energy challenges, but not without addressing this significant opposition from the public. So in line with these challenges, Alex, do you want to talk about some 5 difficult tasks required to achieve net zero goals?
I sure do. Thanks, Jess. Dr. Shankar outlined 5 items that we must address going forward: nuclear, long-duration storage, increased permitting turnaround time, clean energy education, and the need to build out our infrastructure. Jess did a great job focusing on nuclear, but I'm going to add a few more figures for some context. So in 2019, nuclear made up 9% of the electricity energy capacity, but 20% of the energy generation in the United States. So how is this discrepancy possible? Nuclear power plants run 24/7 with very short refueling periods every 5 years. This makes them very reliable compared to intermittent renewable sources. Additionally, they have small footprints, are safe, and beat out solar and wind with respect to life cycle carbon emissions. So a lot of people are looking into small modular reactors. These reactors can be built in factories and may come online and able to aid decarbonization efforts. Additionally, they're going to contain a lot less fuel in case they melt down. Now, alongside nuclear is long-term storage. Long-term storage is needed if we're going to have, be able to save any of the excess of renewable generation from several months into winter, or even just from the middle of the day towards peak demand. I just got back from RE+, which is Renewables trade show in Las Vegas, and some of the most exciting tech that I saw when I was there was related to energy storage. Now, there are several companies working with flow batteries that can release electricity between 3 to 24 hours. This is a really large step forward when compared to lithium ion, which was traditionally 12 to 4 hours of release time. So this is going to help us to eliminate the duck curve that Jess discussed. Additionally, there are a lot of energy storage types like pumped hydro, which have been around for hundreds of years, and the newer stuff like compressed air storage and solid state redox reactions, which can store energy for months. And, it's pretty exciting to see, considering that a lot of this tech has been talked about for years, but not financially viable. And more of that is becoming viable and technically feasible, and it's here now, and we can actually use this stuff. That said, permitting and education are continuing to stand in the way of quick, responsible renewables and infrastructure development. Permit times need to be reduced, and we need to cut through a lot of that red tape so that we can get these projects up and running quick. Additionally, education is needed to bring more technical knowledge to public utilities, grid operators, and developers. Currently, the economics of the grid are focused around small upfront costs with variable fuel costs throughout the life of the project as, electricity demand changes. Moving forward, we're going to see higher upfront costs as, you're installing a solar plant with on-site long duration storage. That's got high upfront costs, but it doesn't have continuing fuel costs because solar's free as far as fuel goes. You're going to have some operating costs here and there, but this completely changes around the capital structure. So now we need to educate our grid operators and have them change the finances of the grid. So if we don't do that, we're going to see things like what's happened in California. So California added a ton of renewables online, and they have state legislature that it mandates the utilities to utilize the renewables. So in the middle of the day, when the sun is shining, you have this peak solar output. So they have to turn all of these other plants offline. And then as soon as the sun stops shining, you have an increased energy demand, which is the duck curve like Jess was talking about. And then they have to turn on all of these peaker plants to quickly ramp up to try to meet that electric demand. So now you're seeing rolling blackouts and all sorts of other issues. Now, because the state mandates this, you have to take solar power. So you don't see a market collapse from the solar energy side. If the state didn't mandate that they took these renewables, the grid operators would just stop taking solar. So solar without storage would now be useless, hence the market collapse. This long duration energy storage is going to allow us to not only shift our solar production from the center of the day to the head and the tail of the duck, which are the peak demand in the morning and the evening. The long duration stuff is also going to allow us to take excess consumption during the summer, save it up, and bring it over to the winter. Now the problem is that type of storage is not financially feasible because you're fighting against natural gas and coal prices, which, in terms of daily operating costs, can operate 365 days out of the year and are, relatively financially feasible. So the grid needs to figure out with some sort of way to incentivize long duration energy storage so that we can have these renewables and they actually make sense and they're actually useful, instead of screwing up the grid like we've seen in California and making legislators put all these unreasonable constraints on these grid operators. Finally, our last problem is the grid itself. So we need to increase 200 to 300% of our electric grid capacity to accommodate our growth in the coming years. Now, electrification is great, and we want to transition everything towards, renewable clean energy, but our grid isn't ready for that. So we need to be able to build out our grid so that when we're electrifying, we're replacing it with renewables and our transmission lines are up to date and we're not stressing the grid and putting too much stuff on all of this.
As we heard, there is still a lot of work to be done in order to meet the net zero goals we have set for ourselves. While the challenge is not an easy one by any means, I feel hopeful that these issues are finally at the forefront of conversations, and many people do realize how vital it is to invest in solutions. So I really look forward to hearing additional seminars that address this topic, as well as the current capstone projects that we are all working on to advance sustainable development in the energy sector. So thank you all for joining us for this first installment of Zoomcasts, and we will see you next time. Thank you.